Começar esse curso. Então, esse curso é uma... I'm sorry, I'm going to speak in English, of course. This course is an introduction to geometric invariant theory. And the question we will be concerned with, that's what the theory is about, is a general question. So given an algebraic group, G acting on a variety X, okay, when and how and in which way is there a structure of variety for the orbit space. That is, for the set of orbits for this action. Okay? So in this course, we're going to see some criteria and cases and situations when you can give a natural structure of variety to the orbit space. Okay? So this course, I'm going to divide it in 5 parts. First part is an introduction. Second part, I'm going to talk about finiteness of invariants, or finite generation of invariants. So these 2 lectures are going to be today. In the third part, I'm going to talk about quotients and orbit spaces. Okay, so that's where I'm going to construct this structure of variety for the orbit space. In the fourth part, I'm going to talk about a stability criterion. Okay, and finally, I'm going to talk about examples. Okay, of application of the stability criterion on of constructing this structure of variety. Okay, so let me start with a very simple example to show that not always can you do that in a natural way. And the simple example is very simple. You take the general linear group. So, as Bertrand talked about, the group of invertible matrices of determinant non-zero. I'm always going to work as I'll be concentrated on the geometric aspects over an algebraically closed field. And we consider X to be the affine space. And the natural action I'm going to consider is just multiplication. So you pick a matrix, you pick a vector, an element of X, view it as a vector, as a column vector, and then you just multiply. Okay? So in this very simple example, you have that the orbit space consists of just 2 orbits. Right? So 0 is always taken to 0. And if you have a non-zero vector, you can take it to any non-zero vector by choosing A appropriately. So AN decomposes into these 2 orbits. So you have here a finite set with 2 elements. And of course, there is no natural surjection. That is a morphism. Let me put it this way. There is no natural surjective morphism from X to Y. Okay? So there is no morphism in this case taking a point to its orbit. Okay? Because this is irreducible, this is not. Okay? So in this very simple example tells you that not always can you find this structure in a natural way. So in a natural way, I mean such that this map here is a morphism. Okay, so now let me talk about the question itself. So why is the question important? Okay, so it's important in at least two ways. First, we can, by means of quotients, try to study algebraic groups. All right, so Bertrand has already talked about linear representations of a group and about structures that can be derived from these linear representations. So a linear representation is an action on an affine space. So, I mean, if you study these actions, you are studying algebraic groups. But also, it's the main method of constructing moduli spaces. In algebraic geometry. Okay. So what are moduli spaces? So, for example, MG. So this is the space of projective, smooth, connected curves over a given field of a certain genus. Okay? So there is a space, a variety parameterizing these curves that we call the moduli of curves MG. Another example, more simple maybe, is the projective space of hypersurfaces. So these are hypersurfaces of Pn of degree d. Okay? So in fact, some people prefer to call these kind of spaces parameter spaces because they parameterize concrete structures. So hypersurfaces are given by an equation. Right? And spaces parameterizing abstract structures like curves that are not embedded anywhere, moduli spaces. But of course, it's a very abstract separation. There is no concrete criterion to distinguish what is abstract from what is concrete. So I'm going to call everything moduli space anyway. So let me talk a bit about MG, because the concept of moduli actually came with the study of curves. In fact, the term moduli appeared in a paper by Riemann, in a seminal paper in 1857. So what he wrote is that a curve, or I'm paraphrasing here, but a curve of genus G depends on 3G minus 3 moduli. So he wrote in German, and moduli appeared in Latin, though. Okay, so it's the first usage of that I know of the word moduli was in this context. What Riemann wanted to say is that a curve of genus G depends on 3G minus 3 parameters, and in fact, one can show that this is a variety of dimension 3G minus 3. Okay, for G at least 2. And how do we construct MG? In fact, the first construction was analytic over the complex numbers. It was given 100 years after Riemann made this statement. But the construction using algebraic geometry follows by the usage of GIT. So let me just point out how this is done, and very briefly and very vaguely maybe. But how to construct mg. So you're going to see that the construction of mg is connected to answering this question here. And that's as follows. What you do, you consider a curve. So, I mean, projective, smooth, and connected with genus at least 2. Okay? And we consider the canonical divisor, or a canonical divisor. Okay? So, since the genus is at least 2, this is going to be ample. In fact, from Riemann-Roch, it's easy to see that 3K is very ample. So it gives rise to a map from C to projective space, which is a closed embedding. Right? This N here can get from Riemann-Roch again. It's 5G minus 6. Okay? So now you have an embedding of your curve, so you can look at the equations defining the curve. That is the ideal of the image. So that's phi. So you can look at the idea of the image inside the coordinate ring. Okay? So now I have something concrete. You have equations. Of course, I mean, depending on the curve, the generators of this ideal will lie in certain degrees and other degrees. So it's not very homogeneous in that matter. But as a fact, is that there is an integer, d, depending only on g, such that two things. First, if we look at the part of degree d on I, so the homogeneous forms of degree d that live on I, you have a vector space which has dimension m, which is independent of g. In fact, you can, again, by using Riemann-Roch, derive this. Okay, so this, for once, that is the dimension of this vector space depends only on G. And second, that the image of C is given by the forms of degree D. Okay. So you see that if you pick this vector space now, that it defines the image. So what we can do, we can associate to C a point I of D in the Grassmannian of m-dimensional subspaces of what I'm going to call W, and W is the homogeneous polynomials of degree D. Okay? So you have this association there. Of course, not every subspace here will come from an ideal. So we're looking at a subset. Which the set of subspaces of dimension n, such that W prime is ID for some C. Okay, so we view this inside the Grassmannian, and the fact is, we can show this, that H is locally closed. So it's a variety. It's a parameter space for what we call tricanonically embedded curves. Tricanonically because we're using 3 times the canonical. But so we have this concrete way of viewing the curve, but we made a choice. In fact, to get phi, we chose a basis of the space of sections of the tricanonical line bundle. Okay? Because otherwise we're going to get a map just to the projectivization of this space here. but we're taking a basis of that, and then we get a map to Pn. So there's a choice involved here, and any other choice is different by a linear transformation. So this is defined only up to a linear transformation. Okay, so that means is that if we take the group of linear transformations, the group of automorphisms of Pn, this is also denoted PGLN. So these are the matrices, invertible matrices of size n plus 1. Modulo and equivalence, where we identify two matrices if they differ by a constant. Okay, non-zero constant. And so what we have is an action of PGLN on some varieties of Pn. In fact, there is a natural map from GLN plus 1 to PGLN. Just take an invertible matrix to its class there. It's a surjective map. So if we're interested in orbits, and that's what we're interested in, we might as well use GLN plus 1. So we have an action of GLN plus 1 on projective space. This action lifts to an action on the cone. Right? So this will act on the space of forms, which is the dual space. The action is linear, by the way. So it will act on the space of degree 1 forms, and thus on W, right? The space of polynomials of degree D. And if it acts on W, and it acts linearly, it takes subspaces of dimension M to subspaces of dimension M. Thus on the Grassmannian of subspaces of W. And of course, I mean, it acts on H as well, by the very definition. Okay. So Mg as a set, the orbit space of H under this action. Okay, so I have it as a set, and if you want to give it a structure of a variety, we might as well try to answer that question. That is, to try to give it as a structure, a natural structure, as a quotient. Right? And that's how actually this is constructed, Mg. Okay, so that's just to give an importance of this question for algebraic geometry. In fact, it's the main tool for constructing moduli spaces. Most of the constructions are done this way. So it's useful in geometry. Now, at around the same time, Riemann was making a revolution in geometry. And throughout the second half of the 19th century, invariant theory was evolving. And it was in the mainstream of mathematics. I mean, a lot of mathematicians were interested in the subject. So I wanted to state the main problem of invariant theory. And because the solution of it will be the answer for that question. Okay. So before doing so, let me recall something that Bertrand talked about. which is a linear representation. So let's pick G, an affine algebraic group. Okay. And always over an algebraically closed ground field, I'll say that linear representation of G is a homomorphism of algebraic groups from G, let me call this rho, from G to GLV. So GLV is the space of linear transformations, invertible linear transformations of V on itself, right? Which is isomorphic to GLN, if n is the dimension of V. So it's a homomorphism of algebraic groups where V is a finite dimension vector space over K. Okay? We can consider also infinite dimensional linear representations, but let's stick with those. Okay? So that's what a linear representation is. Simply that. Now, if you have an action of G on V, you have actions on several induced vector spaces. For instance, we can look at the space of polynomial functions on V, right? So given a basis of V is something given in terms of polynomial. It's the same thing, since the field is infinite, it's the same thing as the symmetric algebra on the dual space. Okay? So it's a sum of products of linear forms. And we have an action. G acts on this vector space. So given G in G, and of course rho, always, okay, we can consider an F, a polynomial function. We can consider Fg, which is another polynomial function, given as follows. So Fg is a function of V, which gives you this value here. Okay? So you apply G inverse to V and compute the original F. Okay? So you get another polynomial function, and we get then sort of an action of G into the vector space of polynomial functions. It's easy to see that the way it's defined, that the action is linear. So you get a linear transformation of KV. Okay? Now this is infinite dimensional K of V, but you see that if you have that F is homogeneous of degree D, then F of G is also homogeneous of degree D. Okay? That's easy to see. And then what we see that is that this action here decomposes as an action on the homogeneous parts. So you have a decomposition here, okay, where KV of D, these are the polynomials that are homogeneous of degree D plus 0, if you want. Okay? And then we have that this action here decomposes. So this action here in me decomposes in linear representations mu D from G to GL AVD. Okay? So in a sense, we're dealing with finite dimensional representations. Okay? Of course, this association here from F to Fg is more than linear. It's actually a K-algebra automorphism. Right? But of course, when we restrict to the degree, we just get a linear automorphism. All right. So, notation now. So notation. KVG. This is the so-called ring of invariants. So these are the polynomials such that when we apply G, we get them back for every G. Okay, so this is the so-called ring of invariants of rho, of the rational or linear representation. Okay? And so that was the main object of a study of invariant theory. So people wanted to produce invariants, that is, elements of those rings, and they wanted to produce a basis of invariants, that is, a finite number of invariants such that any other invariant was a polynomial function on these invariants. Of course, if you have a polynomial on invariants, it's also invariant, right? So, and that was Hilbert's 14th problem. Is it possible? So, is KV of G finitely generated over K as a K algebra? Okay. So that was the problem he posed around 1900. And it was the main object of a study of invariant theory. They wanted to show that, and they wanted to produce the invariants. Okay? And in fact, they had several methods of producing elements of this ring here. In certain situations, they had a symbolic method that produced all invariants. But it was hard to organize these invariants and to show that finitely many of them gave a set of generators. In fact, the main result that was obtained, the main general result that was obtained at that time was a result by Gordon, 1868, who showed the following. So consider the case where the dimension of V is 2. Characteristic 0. And consider G to be SL of V. Right? And rho, so the same V, and actually rho would be the inclusion in GL of V. Okay, so this very particular representation of a vector space of dimension 2, and then what he showed is that if you look at, again, sorry, yeah, if you look at the space of polynomials of degree D on KV, right? So since V has dimension 2, these were called binary forms of degree D, right? We've just seen that there is an action of mu D there, mu D here, X on it, right? And so we can consider the ring of invariants for this action. So the action here is actually the action mu D that is put there. And then what he showed is that this is finitely generated over K for every D. So it was a tour de force, this proof, actually, because he used this symbolic method, which is combinatorially heavy, and very smart reasoning to get to the generators of, to show that there are finitely many generators. So this was called finite generation of invariants for binary forms. Okay. So that was basically it. And then Hilbert came along with new ideas that changed our approach to algebra and proved much more than these. So Hilbert proves in 1890 the following. So pick G equals to SL of W for any space, any vector space W, and consider any action rho. Then KV of G is finite generated over K. I have to put here characteristic 0. Okay, so you see that it recovers this, but much more than this, because we're dealing with any dimension here, and we're dealing with any action, right? Not just this particular action there. So what we're going to do here is to essentially give Hilbert's proof in this lecture. Okay? But before we do that, let me tell you what is known today about this problem. About Hilbert's 14th problem. So there are a number of facts. And the first one is that the answer to this question is, in general, no. So there is a counterexample by Nagata in 1959 that shows you that no, this is not always the case. So when do we get a positive answer? So to show that, or to state that, I'm not going to give the counterexample. It's a bit ingenious. But let me show you when we get positive answers, besides in this case. Right? So, and for that, I need a definition. We say that an affine algebraic group is reductive. So this definition was given by Bertrand. If its unipotent radical is trivial. Okay, so that's one of the definitions. Second, linearly reductive. There are different ways of making this definition. I'll choose one. If for every linear representation we have this condition star that holds, that for every linear representation and for every V in V, non-zero, invariant under G. And by this I mean that if I apply G on V, I get V. So that's an invariant vector. There is an invariant functional, right? So V star is the same thing as the forms of degree 1 on V, such that, invariant, same definition, under G, such that f of V is non-zero. Okay? And third, we call geometrically reductive. Okay? If the same thing here, that is, for every linear representation and for every invariant non-zero vector, there is a homogeneous polynomial of degree d, invariant, non-zero, but well, invariant of degree d, such that f of v is non-zero. So instead of requiring that I have a form of degree 1, I just pick any d. Okay? So there are these three notions. And what Nagata showed is that for these groups here, the answer is positive to Hilbert's problem. So the theorem by Nagata was that 14th problem, yes, for geometrically reductive groups. Okay. Now, what's the connection about all of these notions there? The connection is the following. So we have here linear reductive. It implies, of course, geometrically reductive. Mm-hmm. It can be shown that geometrically reductive implies reductive. This was proved by Nagata. Again. Okay. It can be shown also that in characteristic 0, that follows from works of Weil, that reductive implies linear reductive. Okay. So in characteristic 0, all three notions are equivalent. But in positive characteristic, what we get is only this. So, or in characteristic 3, there is. So star was a conjecture by Mumford, shown by Habush in 74. Okay? So then geometrically reductive is equivalent to reductive. So the answer to 14th problem is yes for reductive groups. And there are many, fortunately, there are many groups that are reductive. And for instance, GLN, SLN, PGLN are reductive. There's another way to view linear reductive groups. I mean, there's an equivalent definition, which I state as a proposition. So an affine algebraic group is linearly reductive if and only if every rational representation of G is completely reducible. That is, decomposes as a sum of irreducible representations. Okay? It's not that difficult to show this. And this connects to actually what Bertrand said. He mentioned that in characteristic 0, reductive is equivalent to this, right? Sorry. Yes, yes. So we are in characteristic 0 and reduced, yes. And yeah, I'm sorry, I always forgot to put the here. So reduce and smooth, so equivalent. Yes, thanks. No, I'm just going to deal with smooth, so reduced algebraic groups. Right? Well, no, let's leave it smooth, because I'm talking about characteristic P here, right? Let's put it smooth. Yes?
Are there any statements of the form saying that the rank of the group doesn't divide the characteristic of the field and then reductive implies linear and reductive? Or something along those lines? I mean, is it known when reductive implies linear and reductive?
I don't know. So what's that, Udo? So yeah, I don't know. I actually don't know. You might, yeah, talk to him later. Yeah. So what I want to do now is actually, I'm not going to prove finite generation in general. What I'm going to give you is something that is very close to what Hilbert did in 1890. Right? So I'm going to give you basically Hilbert's original proof. Sorry? Yes? Geometrically completely reducible. Right, yeah. Yeah, I'm working with algebraically closed fields, so yeah, don't really know. And I'm going to even restrict a little more. I'm going to work with characteristic 0 now. So Hilbert's proof there is a nice write-up of that, if you want. At least I like it. In a book by Sternfels called Algorithms in Invariant Theory. So he gives Hilbert's original proof. I will give you something slightly different, because I'm going to view the proof as basically two theorems. First one saying that SL of W is linearly reductive. So I'm going to show that in characteristic 0, right? Because in general it's not true. And theorem 2, if G is linearly reductive, then KV of G is finite generated. Okay? You can prove more, but the proof gets a little more complicated in characteristic P. And the methods are a little different. And this will follow Hilbert's original proof. Okay? So let's prove theorem 1. So we have to consider a rational representation. Or a linear representation. Sometimes we also call it rational. Okay. Of SLW. Let's pick a primitive mth root of 1, where m is the dimension of W. So I already start with a problem in characteristic P, because not always we have that. Okay, so let's view psi in SL of W as multiplication, right? So any vector you can look at the multiplication by psi, and since it has dimension m, right, the determinant is psi to the m, which is equal to 1. So it's a natural element in SLW, and it satisfies, of course, since rho is a homomorphism, that the associated matrix is an mth root of 1. Okay. Now, I mean, if you choose a basis, let's look at this linear transformation here. So if you choose a basis of V such that we may write this in a block diagonal matrix. Where the blocks are Jordan blocks. So I'm using that the field is algebraically closed. So a Jordan block is something of the form, with 1s here in the upper diagonal and 0 elsewhere. Right? But what we know is that since this is true, we know that the nth power of this block is 1. But if you look at the nth power of this block, what you're going to get is the following. So if I call this j and raise to the power m, what you're going to get is this. Right? So you see that if alpha is non-zero, and it must be, and m is non-zero in K, which is the case in characteristic is 0, then this implies that the Jordan block has to be of size 1. Okay? So this means that the matrix is diagonal, or diagonalizable. Notice also that, of course, the power of here is 1. So this must be a power of psi, which is the primitive root. Right? So if we set Vi to be the eigenspaces, right? So the elements on V such that rho psi V is a multiple of V, right? So what we get is a decomposition of V into these eigenspaces. And then we get the decomposition of the representation as well, because since this is multiplication by a constant, right, so it commutes with every other element. And if that's the case, then this also commutes. And then you see that this sends VI into VI. Okay, so you have a decomposition of the representation in several representations. And so rho is a sum of these representations. And it's easy to see, so exercise, if the condition star holds for rho I, it holds for rho. For every I, of course. Okay, so the condition star, meaning the condition that, for every invariant vector, you have a linear invariant form that is non-zero at that vector. Okay, so the condition of being linear reductive. So it's very simple. You just pick a vector and then you write it as a sum, right? And each summand is invariant, and at least one is non-zero. You find the linear form for that one, and then you just extend to the whole space by letting it be zero in the rest. So that's the proof. Okay, so we may assume then rho of Xi is equal to Xi for some I. Now, let's try to prove star. So let's pick V naught, an element of V that is invariant under SL of W. So V naught non-zero. Okay. And then since it's invariant under SLW, of course we must have these as well. But this is multiplication by Xi. Star. Right, so I'm going to put star here. I erased, I'm sorry. So star, what we have to show is that for every V in V, G invariant, so invariant under G, right, non-zero, there is an F in V star invariant under G, right, such that F of V is non-zero. Okay? So that's what we have to show.
Quite confused by the whole theorem. Perhaps this is pure crap, but just in any ways I'll ask it. So there's in characteristic zero you have this non-degenerate invariant pairing between V and V star, G acts in both, as representations.
Mm-hmm.
Why isn't this just the pairing that you get on cohomology? On the G cohomology?
A theorem that you get on G cohomology?
Yeah, on the zero cohomology. You still get this pairing and
for SLW.
yeah,
I mean,
so for the first statement.
Yeah.
Any reductive group, zero.
Right. Could be, yeah, but I'm trying to give a more elementary proof here. Or at least I think it's more elementary. So that's, in fact, I'm still trying to connect it to Hilbert's proof. Hilbert showed something slightly different, which is what I want to get now. Right? So in this situation here, so actually you see that we must have, since there's an invariant vector, that this must be 1, right? And then rho extends in a trivial way to an action of GLN, to a linear representation. To a linear representation of GLN, GLW into GLV. So it's simply what you do is if you pick an element of GLW, you write it, let me separate here, you write it G as C of H, where H is this SLW, right? And then you just define rho tilde of G to be rho of H. Okay? In fact, you can show that it extends in even before that, but after this reduction, it's quite clear how you do it. Okay? So now we get to the actually, what Hilbert did. So we have an action, this rho tilde of GL of W into SL of V, and you have this space V naught in V. This is vector V naught, non-zero, such that it's invariant under SL of W and also under GL of W, okay, by the very construction there. Okay, so that's when Hilbert used something that was widely known at the time, which is called Cayley's, now used, Cayley's omega process. So what's that? So it's the following. So that's a defect that I'm not so sure I will be able to prove. Is the following. First, something else we need to do. Of course, if you have a non-zero, V naught here. Okay. Of course, if you have a non-zero vector, there is a functional such that f of V naught is non-zero. Right? What we want to get is something that's invariant. So we consider the action. So here we have GL of W times V. You have an action that takes G and V to GV. That's notation for rho of G or rho tilde of G V. Right? And here we have our F that goes to K. Okay. Now, since I've passed to GLW, this is an open subset of, by choosing basis, of a fine space of dimension n squared, where the coordinates I'm going to denote by Tij. Right? So one coordinate for each entry of the matrix times an. And here let me denote the coordinates by xi. Okay. So n is the dimension of V. So this is a principal open subset here, given by the determinant being non-zero. And we have here a regular function defined on this open set. So that means that there is an integer L such that the determinant of Tij to the power L times times this function here, which is f gv, right? This composition here. So this is polynomial on T, on the Tij, and on the XL. Okay? So you extend it to a polynomial. And then you do this construction here that I call, let's call the omega process. That is, you look at an operator I'm going to define soon, applied to this polynomial. So we get another polynomial, and we set t equals to 0. Okay? So the statement is that this is an element of V star. So it's a linear form just as V was, and invariant. Under GL of M. Okay? So this was one of the methods, they had several, that people used to produce invariants. So just to start with any form, any linear form, or even a form of degree D, I mean, it's more general than that. And then you do this construction here, make t equals to 0, and you get something which is invariant. Okay? Now this, today, I mean, we would do, what we would do is to use a Reynolds operator. So this is a poor man's substitute for the Reynolds operator. I'm not going to talk about this. Okay. So that's what Hilbert used at the time. So let me define what this omega t is. You can find this description in the book by Sternfels. It's very well written there. So this is the determinant of the matrix of operators of these partial derivatives. Right? So what does it mean? It means the following. It means that, so we apply this into a polynomial in the variables Tij, or in other variables as well, but at least Tij. And what we get, we use the rule of the determinant. So we look at sigma in the symmetric group, in the same permutation group. That's the sign. And here we have the partial derivative given by sigma 1 dt m sigma m. Okay, so it's this linear operator where you take all these derivatives. Okay, and then what we do, well, there are two facts about this omega t that I have to talk about, but let's use this fact that this is an element of V star. And what you get when you apply it to V naught is the following. So here we have the determinant to the power L. Here I have G. And now I'm specializing V to V naught. Equals to 0. But what happens is that V naught is invariant. So that means that G of V naught, which is rho of G of V naught, is V naught. Okay? And now we have a constant here. It doesn't depend on G or on T. So I can put it out because this is linear. Okay, so we get this. Now f V naught is non-zero, and the proposition, or the fact, that I'm going to prove later, is that omega t to the power L, determinant of Tij to the power L, is non-zero. In fact, is a positive integer in a sense, because you have to multiply by 1. So again, we're using characteristic 0 there. Okay? So using this, since this is non-zero, this one is non-zero. And then you get your F naught. Okay? So that's Hilbert's idea. But in fact, everything here was basically already known to the people in invariant theory back then. I mean, the Cayley's omega process was widely used. Right? But in any case, that's the proof of theorem 1 using these ideas. And now let's move to theorem 2. I'm going to use this once again, such that f of v is non-zero. Okay? In fact, Hilbert's proof is a bit different, but I'm decomposing 2 because I want to use some results, some intermediate results. And in fact, I want to use this theorem to prove the following proposition, which is going to be used in the proof of theorem 2, right? Which is the following. So pick G a linearly reductive group, rho a rational representation or linear representation, just as before. Let I be an ideal in the ring of invariants. Right? Then, if we extend this ideal and intersect with the ring of invariants again, we get back I. Okay? So let me show this. So proof. So of course we have the inclusion. This inclusion here is okay. We have to show this. Okay. So we pick an element. In here. So that means that we can write f as a summation of fi hi, right? Or fi is in the ideal, and hi is in this ring, kv. Okay. Let me say that d is the maximum of the degree of the hi's, and let me call E d plus the maximum of the degree of the fi's. Okay. So we get a linear map from K V, but just to the polynomials of degree at most d. I want to get to have a finite dimensional space here. So let's say that we have a sum of p elements here. So we get a map by applying F1, Fp. Okay, so that means that I take a p-tuple here, and I pick the linear combination. All right? Okay. So you see that, of course, we can apply this to H1 up to HP to get F here on the other side. Okay. we have an action on this space to the left, right, on this space there. And the action is very simple, of course. I mean, we pick B1 up to BP, and G, that's B1G, BPG. So we act factor by factor. All right. And so we can consider the subspace generated by the orbit of H1, HP. Okay. This is going to be a G invariant. Right? Because the generators are taken to themselves. Okay. So we have a linear representation of G on W, and phi of W is actually a one-dimensional vector space, the space generated by F. Right? This is because every generator, right? So this is because F is invariant. So F is equal to Fg, right? F is invariant. Applying G is algebra homomorphism, so I can split it here. Fi are invariant. Right? And Hij are not, but what we get on this side here is simply phi of H1 HPG, right? By the definition. So you see that every generator is taken to F, so W is taken to this one-dimensional subspace. Okay. If that's the case, we can define a linear functional. So W is there, and let psi be the linear function defined in this way. So psi of W is an element of K such that multiplied by F is phi of W. Okay, so I pick this constant here. So we have an element of W star, and this psi is G invariant. Right. So it's basically the same idea involved in here, right? Or the fact that this phi is a G map because these Fi's are invariant, or G invariant. So this is easy to verify. And then we apply the fact that G is linear reductive. So we have a linear representation of G on W star. So it means that there is a form on the dual of W star, but that's W. Right? So there is a W in W invariant, such that psi of W is non-zero, and I can choose it to be 1. Okay, so use that the W is the double dual. Right? And of course, W is can be written as B1 up to BP. These BI are invariant. Okay, so that's the meaning of being invariant there, W. And the fact that this is 1 is equivalent to the fact that F is the summation of Fi Bi. And if that's the case, since the Fi are in I, and I is an ideal here, then this means that F is in I. Okay, which is what we wanted to prove. All right? Okay, so now we're ready to prove theorem 2. We're going to use this, so let me leave this there. And come back to here. So proof of theorem 2. So that's Hilbert's proof. So what we do is the following. We pick J in K of V, the ideal. So that's what we want to prove, right? So we pick the ideal generated by all homogeneous invariant forms, invariant polynomials of degree positive. Okay? So we consider elements of here, right, that are homogeneous, and we pick the ideal generated by them. And then we may write J as F1, Fp, right? Where these Fi are among the generators here. So these Fi are homogeneous and invariant, where di is positive. Okay? So you write it this way. Of course, you have that. So what we want to show, so we're going to consider R to be the ring generated by these polynomials inside K of V. In fact, since they are invariants, and polynomials on invariants are invariants, so that means that R is contained in KV of G. And what we're going to show is that equality holds. So then the ring of invariants will be finally generated. Okay? All right. So we do the following. We consider, since these Fi are invariants, we may consider the ideal generated by them in the ring of invariants. Okay, so this is in K of V, but now I'm considering the ideal generated in the ring of invariants. Of course, we have that J is the extended ideal because of this equality here. And let's show then this equality here. So take F in KV of G. So F is a polynomial. It's not necessarily homogeneous, but it can be written in as a sum of homogeneous polynomials, right, in a unique way. G preserves the degree of the polynomials. So it means that if F is invariant, its homogeneous parts are going to be invariant. And I just need to show that these homogeneous parts are in here, in R, because F is the sum of them. Okay? So, to show F is in R, we may assume that F is homogeneous. Okay. If the degree is 0, then of course F is in K, which is contained in R. So that's no problem. So we're going to assume that the degree is positive. And reason by induction. So we're going to assume that for any homogeneous polynomial of smaller degree that is invariant, this polynomial is inside R. Okay? Now, this F is in, so it's invariant, right? And as such, since it's an invariant homogeneous polynomial, it's one of the generators of positive degree. It's one of the generators of J. So F belongs to J intersect KV of G, which is I KV intersect with KV of G, right? And from there, we get that this is I. Okay, so we use the proposition. And then we're basically done, because I is generated by the Fi's. Right? So we have that F is the summation of AI Fi for some AI invariants. Right? Because I is generated by these inside the ring of invariants. Right? And since F and Fi are homogeneous, we may assume that AI are homogeneous. Because the homogeneous parts are invariant. Right? Now, since the degree of Fi is positive for every I, that means that the degree of AI, well, we can choose in that way, right, is less than the degree of F. So they are invariant, they have a less degree, so that means that these AIs belong to R, and thus F belongs to R. Okay? So that's the end of the proof. So this last part is quite simple, in fact. But it was the reasoning that was most striking at the end of the 19th century. I mean, the first part, which might look more mysterious to us because it uses the scaling process, and I'm going to talk a little about it now, was rather understood back then because they used that to produce invariants a lot. What was not understood back then was this. So the fact that ideals in polynomial rings are finitely generated. So that is Hilbert's base theorem that he used exactly to show this theorem 2 here. Okay? So what we find natural today, because it's given in any basic course on commutative algebra, was not that natural then. In fact, it's said that Gordon called this theology because the proof given by Hilbert didn't produce these guys here. They just show that they exist. Right? So what looks mysterious to us was very well understood back then, and what was very well understood back then, the scaling process, might look mysterious to a lot of you who haven't seen that. So let me talk a bit about this omega process. In fact, let me recall this. So the omega process, scale is omega process. So remember that this is omega t. So we're looking at polynomial in these variables. A ring of polynomial in these variables. In fact, it doesn't need to be over a field. You can put a ring here. And we're looking at an operator on this ring here, such that, so let me call this R. So if I pick an F in R, so by definition, this is that summation there. And here I'm going to pick of F. 1 sigma 1. Tn sigma n. Okay, so I'm recalling the definition that I gave. So we have an operator on this ring. It gives you another polynomial. Now, there are two facts that I mentioned. I'll first look at this one, which is the fact that, proposition, if I apply this L times to this polynomial, to the power L, so notice what happens. The determinant is a homogeneous polynomial of degree n, because it's an n by m matrix. So here we have a homogeneous polynomial of degree nl, and every time I apply omega t, the degree drops by n. So I'm applying it L times, so what I get there is a constant. And the proposition is that this is in Z in some sense. In fact, more than that. Is a multiple of 1, an integer multiple of 1, a positive integer multiple of 1. Okay. So let me prove this. In fact, I mean, there's nothing special about, that's something special, but I can consider other operators. In fact, if I pick any polynomial, G, let me write it as this. So I pick the summation, and here I'm going to put all the monomials. There are m square variables. Okay. And I'm summing over all nu. Okay, so that's the expression of the polynomial. This a nu is in k. And I can consider omega of g applied to any f. And this is by definition the summation of a nu. So what I do is I replace this Tij by the derivative, the partial derivative with respect to Tij. So what I get here is this. So this is the sum. Oh, let me write it everything. The derivative of f. And then here I'm going to put dt11, nu11, dtmm, nu mm. Okay? Where this is the sum, right? So I sum over all nu's, and this is the sum of nu ij. Okay, so in that sense, this omega t is just short of omega determinant of Tij. Okay? So there are more operators you can consider. And what can you say about them? Well, they are linear. Of course. They are linear. Linear. If you have a product of G1 and G2, right, this is the same thing as applying one and then the other. This is quite simple because these partial derivatives commute between themselves. Right? So it's easy to check. Oh, there are more properties, but let me concentrate on this here. That's what I'm going to need. Because now I want to look at this. So I'm looking at, of course, omega TL, which is omega determinant of T to the power L. I'm applying this L times, so it's the same thing as omega determinant of T to the power L, using this property here. Okay? So what I'm doing is actually applying omega of some g to g itself. Right? And the claim is that if g, the summation there, which I'm going to abbreviate like this, right? But it's the same description. If g is homogeneous, then when I apply omega t, omega g to g, that's the summation of a nu square and then these factorials here. Nu 1, 1 factorial up to nu mm factorial. Okay? So the sum over all nu's of that. All right. Let's see how to use that first. And it's easy because the determinant, the expression of the determinant, you have the coefficients are integers. Right? This minus 1 to the sigma. Right? So the determinant of t, yeah, if I call this j, this is actually in z. Right? And then what this tells me is that this belongs to n times 1, of course. Right? Because I'm taking the square here. Right? So nothing cancels out. Even if I have negative coefficients, they become positive here. Everything is positive. I'm summing positive things. And at least one of them should be positive because this is non-zero. Okay? So from the claim, this is the end of the proof. Now the claim is easy to prove. It follows from a simple fact. Right? So we want to apply omega g to g. G is a sum of monomials. So let's look at what happens when we apply to monomials. And that's the third property I forgot to mention here, is that omega g1 plus g2 is omega g1 plus omega g2. Right? So I'm applying to g. Omega g is linear. So I can write g as a sum of monomials, and I get the sum of the applications. And then I can use this. So basically what I have to see is that if I pick a monomial and apply it to another monomial, right? So nu and nu prime, what do I get? Well, remember that it's homogeneous, so if they have the same degree, that's the situation we're looking at. And then it's easy to see that all the powers drop, and you get the product of the factorials if nu is equal to nu prime, and you get 0 if nu is different from nu prime, because at least one of the nu i's will be bigger than the corresponding nu prime I, and then you're going to be differentiating more than you should. Okay? So it follows from this. All right, so that's one of the facts. I might have a lot of time. Let me try to sketch the proof of the second fact. And the second fact is known as they have names for that back then. It's in fact a way of producing invariants. And the fact that I want to show, it's a theorem known as the second main rule for the omega process. And it's the following. Let's consider so we're going to consider two rings here. R is going to be K of V, which is K of V1 up to Vn. Right? So I'm going to use the notation here in Sternfels. So these are the variables. And then we have the other ring. Oh, I call this R, so let me call this A. and we had R. Okay. And what we can do is we can consider, I'll use this, TV. Right? So what this means is the matrix Tij applied to the column vector V1 up to Vn. This will give you another column vector, right? And yeah, so that's it, this column vector there. Okay. So that's the notation. If I pick an F in A, that is in KV, I can consider F of TV, right? So what I pick is I pick each entry of this column vector and replace in the corresponding part. Okay. Now let F be in here. Let P and Q be integers, arbitrary. Then let's see how I'm going to do that. I PQ of F, which is omega T P, the determinant of T to the power Q. So I'm going to apply this to a polynomial in T, right? And more than a polynomial in T, it's a polynomial in T and V, which is this. Right? So as I said, I can evaluate F on T of V. Right? I'm going to get a polynomial on both variables. And I multiply by the determinant to this power. And then do this operation. I'm going to get a polynomial in T and V. And then I make it T equals to 0. And the conclusion is that this is a relative invariant. So I have to tell you what this means. Right, in our situation, we were applying this when P equals to Q, right? And then we get an absolute invariant. In fact, what it means is the following. So, more precisely, if I pick this I, P, Q, and apply it of F. So this is a polynomial again in this ring here, in A, right? Because it depends just on V. And if I apply this to T times V, so I do the same thing before, but this time what I get is the determinant of T, P minus Q, I, P, Q of F applied to V. Okay? So it's a relative invariant of degree P minus Q. And when P equals to Q, you get the same stuff. Right? So you see that this becomes an invariant under the action of GLM, as we wanted before. So that's what we have to show. This is statement here, commutative algebra. And to show that, we need the first main rule. Right? I mean, the first must come before the second. So what's this first main rule? Is the following. So now we're going to look at another ring. Let me call this S, which is the ring where I have S and T. So S is a set of variables, Sij, from I and j, varying from 1 to n. Okay? So just as t, but another set of variables. And then the first main rule is the following. Right? If I pick, let f be a polynomial in t, in one set of variables, then if I apply this omega process to f of st, so a similar notation, I'm there multiplying the two matrices, S and T. I'm getting another matrix, and then I'm replacing where I should replace, here in F. Right? So this f of st is now a polynomial in all these variables here, S and T. But I'm applying just the omega operator T. And the conclusion is that this is the determinant of S times omega st GST. Right. So I have to explain this, but I guess not much. I mean, what I'm doing here, if you want, this is omega t, omega u, if you want, another set of variables, and then you substitute. Okay? Right? So I pick another set of variables if you want, apply the omega process, and then make this substitution. That's exactly what it means. Okay? And if I want to do it with S, then it's okay. I get the same stuff, but what pops out is T. Okay, the statement. Okay, now let me do the proof of this. So that's, I don't know if I'm going to have time to prove everything. In fact, I'm going beyond what I expected I could do anyway. But in a sense, I mean, it's quite natural to use this omega process to show that something is invariant, because here, you see, I have a multiplication inside the group. Right? And we are understanding the behavior of omega t with respect to this multiplication. This determinant pops out. Right? And that's basically what we want here. So you see that we're not that far from proving this. Okay? Okay, so let's prove this identity here. And the second one is similar. So we look at this left-hand side here, right? So this omega t is a sum of derivatives, of partial derivatives applied to this. In fact, we have one of these derivatives, oh, it's m, right? Is this. Okay, so this appears. Oh, sorry, not phi. I'm sorry, I changed the notation. Right? So this is one of the derivatives that appear here, right? We have a sum of plus or minus these guys here. Okay, and what we get. So the idea here is, of course, to apply the chain rule. Right? I have a multiplication here, S and T. Right? So I'm taking the derivative with respect to T. But first we have u here. So this is the following. Okay, let me see this. So this will be the summation of tau 1, tau m, from 1 to m, right, of the derivative of m of phi, but with respect to u, and then we replace u by st. Right? So I'm going to derivate with respect to u. Oops, sorry, again, f. So I'm going to derivate with respect to u. U, tau 1, sigma 1, derivative of u, tau m, sigma m. Okay? And then I'm popping out this outside. So times s, tau 1, 1, s, tau m, m. Okay? So this is the chain rule. Right? So we take the derivatives of f and then the derivative of what's inside here. Right? Since what's inside is linear on t, then, and we have all these derivatives, what pops out is m of these variables s, I, j. Okay, so this is part of the left-hand side. Of course, we have to sum this. So we have to sum over all the permutations. So this sigma here is a permutation in Sn. Okay. And if we do, right, so this omega t, fst, is simply this summation over the sigmas of minus 1 sigma of this guy here. Star sigma, let's put that way. Okay? So we do the same thing on the other side, right? And then we have a double sum. A sum on these tau i's and a sum of sigma. So we interchange the sums, right? So this will be equal then to the summation of, should be sigma and then this summation here, but I interchange tau 1, tau m equals to 1 up to m. And this pop out now. And then I have the summation inside, which is on sigma, minus 1 sigma, and here the derivative of f with respect to u, and then I substitute. And here I have this du tau, tau 1, sigma 1, tau m, sigma m. Okay? Now what happens is that if the tau 1 up to tau m are not distinct, then this part here is 0. Sorry, this part here is 0. Right? It's like a determinant where I have repeated rows. Okay? On the other hand, if you have a permutation, then what we get here is then the summation of tau 1 up to tau m equals to 1. So what I'm saying is that this sum here, we can just consider that in the case where these are distinct. Okay? So distinct. Right? S tau 1, 1, S tau m m. And then what we get there is, I'm sorry, I'm confused. Yeah. So what we get is minus 1 to the sign of this new permutation. So since these tau are distinct, we have a permutation now. Tau that takes I to tau I, right? So we can consider the sign of this permutation, and that's what it appears here. So what appears here, if we replace tau 1 up to tau m by by 1, sigma 1, m sigma m. Oops, sorry again. This is T, U. Okay? So what I'm doing here is, it's again the property of the determinant. I'm changing the position of the rows, right? And what pops out is the sign. But then you see that on this side here, right? So now you have this decomposition here, because this does not depend on tau, just depend on sigma. On the left side, I have the determinant. And on this side here, I have omega of st in f of st. Okay? Which is what I want to show. Okay? So it's just a combinatorial thing. And I don't know if I have time to explain. So this is the first main rule. And now I would have to explain the second one. And the idea is simple in a sense, because what I have to show, so let me try to do this, just a sketch to show this. So proof of this theorem now, second main rule. So I want to show that this is invariant. I have already t here and making t equals to 0. I mean, t equals to 0 means making all the tij equals to 0, right? So instead of putting p here, I'm going to put s. Right? And then this, by definition, would be omega t to p, the determinant of t to the power q. And here I have f of t s v. And this I make t equals to 0. Right? So instead of applying to v, I'm going to apply it to SV and see what comes out. Right? But what you see is the following. Right? So this is the same thing as omega t p. And let me do it that way. So I put the determinant of S outside. Right? And then I put it inside. In which position? This position here. Right? So I'm just using the fact that, right, I'm the determinant here, and the fact this is derivative with respect to t, not with respect to s. So I can put inside. Right? And now I have something very similar to this. Right? So I have a polynomial, which is this one, and, well, I'm actually going to use this here in a sense, because this appears here in the second part. So I'm going to show what I didn't prove. It's a pity, but it's proof is analogous. So I'm going to use this here. Right? And then what I get is that I can put the determinant outside, right, for every time I apply omega t, which is omega s, it's some s, right? But anyway, I mean, the idea is that I put it outside, and I put one determinant every time I have an application of omega t, so I get the determinant, so this is equal to the determinant of s to the power p minus q, right? And then here, omega is this guy here, right? So omega st, and then my function. Is that it? Right, determinant of st, f st, v, and then I make t equals to 0, right? But making t equals to 0, you make st equals to 0. So this is the same thing as the determinant of p minus q, omega t, determinant, oh, I forgot the power here, the power was q, right? Determinant of t to the power q, f tv, t equals to 0. Right? So I have here a product, st, right? And when I make t equals to 0, this product becomes 0 as well. So it's the same thing as doing this. But now this is my function back. So this is I pq of f applied to v, right? By definition. Okay? So that's it.